The mixed-dimensional periodic Anderson model (PAM) is proposed to simulate the band structure of U2, combining unidimensional conduction electrons and 2- or 3-dimensional pholectrons. By varying the pholectron level delta-F, the model exhibits a transition from 2-dimensional rectangular-shaped Fermi surfaces to mixed-dimensional ones, consistent with LDA plus U and LDA plus DMFT calculations for U2. The hybridization parameter VFP affects the shape of the 3-dimensional Fermi surface and changes the nesting property. The spin susceptibility, calculated using the random phase approximation (RPA), reveals antiferromagnetic fluctuation with the wave vector around 0, pi, 0. The Eliashberg equation is solved to investigate superconductivity, indicating spin-triplet p-wave superconductivity. The superconducting transition temperature is determined by the condition lambda equals 1, where lambda is an eigenvalue of the linearized Eliashberg equation. Numerical calculations are performed for a 64 x 64 x 64 lattice and a Matsubara frequency cutoff of NF equals 1024. The results suggest that the interplay of magnetic fluctuation and superconductivity in U2 is essential for the origin of superconductivity, consistent with experimental findings suggesting ferromagnetic criticality. The model's parameter dependence of antiferromagnetic and ferromagnetic fluctuations is examined, and their relation to superconductivity is investigated. The study finds that the wave vector of magnetic fluctuation is related to the symmetry of superconductivity, and that spin-triplet p-wave superconductivity is stable and can coexist with antiferromagnetic fluctuation. The mixed-dimensional PAM is distinct from the 1 plus 2-dimensional PAM in this regard. Future extensions of the model are proposed, including the inclusion of spin-orbit coupling, magnetic field, and multiple orbitals and sublattices, to identify multiple superconducting phases under pressures and/or magnetic fields. Here is a combined summary of the 4 pages. Recent advances in high-purity crystal growth of U2 have led to a resurgence of experiments in this field. Quantum oscillation, thermal conductivity, and NMR night shift measurements have revealed behaviors consistent with the order parameter D equals kx plus key plus case, similar to the B phase of 3He. This order parameter realizes strong, weak, topological superconductivity in the presence/absence of a 3-dimensional Fermi surface. The paper reviews various studies on U2, including those on quantum oscillations, Fermi surfaces, and superconducting phases. Recent discoveries of a quasi-2D Fermi surface and electron-hole tunneling in U2, as well as the detection of a 3D Fermi surface and strong topological superconductivity, are highlighted. Theoretical models, such as the 1 plus 2-dimensional periodic Anderson model, are discussed to understand the correlated normal state fermiology and topological superconductivity in U2. The mixed-dimensional periodic Anderson model is explored, focusing on the 1 plus 2-dimensional variant, which is compared and combined with the 1 plus 3-dimensional model to reveal general properties. The study reveals that antiferromagnetic fluctuation dominates over a broader range, and ferromagnetic fluctuation appears at a higher pholectron level in the 1 plus 2-dimensional model. Superconductivity is classified by irreducible representations, showing a stable state change from spin singlet to spin triplet at around increment f equals 0.08, associated with the antiferromagnetic to ferromagnetic crossover. The gap function and eigenvalues of the Eliashberg equation are also discussed, providing insights into the nature of superconductivity in this model.